This episode of the Structural Engineering Channel is brought to you by PPI, a leader in engineering exam prep for the PE structural exam. PPI provides expert prep courses and study resources designed to help you pass the PE structural exam the first time. PPI's PE structural course is fully updated and taught with October 2021 code references and includes new editions of their PE structural books. PPI's live online courses include hours of lectures, problem-solving demonstrations, exam strategy sessions, office hours, and a passing guarantee. When you take a live online course, PPI guarantees you will pass, or you can take the on-demand course for free. PPI has helped engineers achieve their licensing goals since 1975. Check out PPI today at PPI2pass.com to see all of the resources available for PE structural exam prep. Again, that's PPI2pass.com.
Welcome to this episode of the Structural Engineering Channel, a podcast focusing on helping structural engineering professionals stay up to date on technical trends in the field and to help them succeed in their careers and lives.
In this episode, we are talking to Alyson Hallander, a product engineer at Schöck, about structural thermal brakes. We talk about some of the benefits and structural design considerations when working with those. I'm your co-host, Matt Picardal.
And I'm your co-host, Kara Green. Let's jump into our conversation of the week with Alyson. Alyson, first, welcome to the show. In your own words, can you please tell our listeners a little bit about what you do daily at Schöck and about the company itself?
Sure. Well, first, thanks for having me on the show today. We really appreciate you inviting me on to talk a little bit about structural thermal brakes. At Schöck, I am a product engineer and project coordinator. So a little bit about what I do day to day. I design structural thermal brake connections for projects throughout North America. So at this point, these are a delegated design item. So it's something that we do take on the responsibility of designing thermal brake connections for projects. And so I do contribute to that. I also regularly travel, meeting with our partners on projects, whether it's architects, engineers, general contractors, just to ensure that everything goes smoothly through the design process and then construction and installation of our products. And I coordinate and lead our education efforts. So just trying to grow awareness of structural thermal brakes in the industry and educate on how they work and how to work with them. But yeah, when it comes to Schöck, so Schöck is a global company with offices in 14 countries, including the US and Canada. They are headquartered in Baden-Baden, Germany. They were founded back in 1962, so have been around for quite a while now. And they manufacture structural focused products. Their primary product is structural thermal brakes, but they also manufacture stud rails for punching shear reinforcement, shear dowels, thermally isolating facade attachments, as well as sound insulation products for concrete stairways.
Thanks, Alyson. Yeah, thermal brakes is something that, obviously we don't design as structural engineers, but it is, it always comes up and in some areas of the world or wherever you're at, we'll specify thermal brakes and whatnot. But it's definitely not something that you'll probably learn in school or whatnot, or if you've been in the profession and you don't specify them, you may not know what they are. For our listeners that aren't too familiar with thermal brakes or thermal bridging, could you give an explanation on that?
Sure. So thermal bridging occurs at any penetration through the insulated building envelope, which creates a discontinuity of insulation and creates a path of low resistance for heat transfer through that thermal bridge. So just to put a visual to it, if you have something like a balcony where your slab extends from that interior slab to that exterior balcony, that's creating that path of thermal transfer, which creates that thermal bridge, where you're seeing significant heat loss through that path or just significant heat transfer in general. And you oftentimes result in these cold surfaces on the interior structure in the vicinity of that thermal bridge. So that's where things like, or solutions like structural thermal breaks come into play. A structural thermal break breaks that bridge. So that's why that's called a structural thermal break. So it breaks that bridge while contributing to the structural integrity of that connection. So in the case of the balcony, that structural thermal break is going to be transferring the structural loads from the balcony back into that interior reinforced concrete structure. It's also maintaining that continuous insulation line along the building facade to provide that thermal, the thermal performance.
No, and that's great. So when you're talking about, your structural thermal breaks and so you're disturbing I consider it a cold path into likely a very warm interior, which is probably likely where this is seen. Are there any other benefits other than maybe preventing heat loss or a cool of transfer? Any other benefits in using structural thermal breaks?
Yeah, sure. So that's exactly as you described it, really what it does accomplish. Aside from just the mitigating the heat loss benefit of incorporating structural thermal breaks, it does, or they do also benefit the building from a thermal comfort standpoint. So when you think about just looking at that balcony example again, if you have a thermal bridge, you're introducing these cold surfaces into your heated occupied space. And cold surfaces, I mean, if you've ever sat next to a cold window, I know neither of you are from very cold regions, but I'm sure you've been in cold places where
Yes.
you sat next to a cold window and it makes you feel cold. So same idea, these cold surfaces get introduced into your interior space. They can make occupants feel cold, and oftentimes they'll respond by cranking up the thermostat and resulting in kind of this imbalanced temperature conditions. So that second benefit, aside from the energy efficiency, heat loss mitigation standpoint, would be around improving thermal comfort. Now, third benefit, and oftentimes this is really a big aspect of the decision of why projects do pursue structural thermal breaks when they're not required to do so by code. But the third benefit is to eliminate risk of condensation on that interior portion of the structure. And so that thermal bridge is, when you're introducing that cold surface into that heated space, the slab or whatever the structure is there, it could be a steel beam instead of that kind of concrete application, but whatever the structure is there can reach dew point and then lead to condensation. Condensation can lead to mold, which can go, unmitigated within your wall assembly, or it can, make itself known if you're seeing mold in isolated areas of your room. So that elimination of that risk of condensation and mold is a pretty important benefit of incorporating structural thermal breaks.
No, and I think that's great, especially since I know a lot of structural engineers do a lot of remediation work where water was a contributor to structural degradation behind facade connections. Do we have, or I don't know if you have any comments, like, has there been any research in a structural thermal break helping prevent not necessarily leaks per se, but almost corrosion behind facade components? Because I know a lot of facade engineers, of course, once everything is enclosed, there's usually like a waterproofing membrane. But if there is like condensation available, past that waterproof membrane, have y'all seen anything in protecting those types of elements, like around the structure?
Sure. So the structural thermal break should mitigate that completely, because you are, really stopping that issue from occurring where you're getting that kind of thermal bridge from happening, where you're getting those cold surfaces on the interior portion of your assembly from reaching dew point and building up that condensation. So the structural thermal breaks certainly solve that issue entirely. Another, not kind of unrelated to structural thermal breaks, but when it comes to facades and just facade connections, another Schöck product does provide that kind of fastener, that thermally isolating fastener to fasten like sandwich type panel facades without creating those really like individual small thermal bridges. So those are kind of the smaller thermal bridges that are introduced in your building facade, your assembly. So they don't need something like this, like heavy structural thermal break at those points. But that product, it does create that structural connection of your facade while mitigating the thermal, or like the points of those tiny thermal bridges where you'd also introduce those kind of condensation points.
Yeah, for those listening through audio, Alyson
Yeah.
kind of just showed some of the samples. Could you go through some of what the structural thermal breaks are? And if you're watching on video, we'll link this on YouTube as well. She can show a sample, but we'll try our best to describe them to our audio listeners.
Yeah. Sorry, I forgot about the audio aspect of things, but I'll try to be as descriptive, visually descriptive about this.
It's okay. It gives us a chance to kind of expound upon our vocabulary and how descriptive we can be.
Challenge. It's a challenge.
So sure. So when we're considering structural thermal breaks, or really just thermal bridges in general, some of those larger thermal bridges, from a concrete perspective, applications include balconies, parapets, and exposed slab edges. And so I've got a sample here, just reaching. This is a sample of a structural thermal break for a balcony connection. I'll just show what this looks like. And in actuality, these extend about 3 feet in the lengthwise direction. About 1 meter, makes sense being a German headquartered company. And then the steel here that we see that extends through that insulation body, this extends out a lot farther. It varies based on the structural needs of the structural thermal break, but just know that that does extend much more than what you see here, where this is cut just to make this somewhat graceful for me to handle. But yeah, so what we're looking at here as far as individual components go, the insulation body, this is 3 inches wide, and this is a neopore insulation. So this is creating the thermal break. And so this is aligned with your wall assembly in either direction, top and bottom, around the structural thermal break. And it ends up being flush with the exterior concrete structure. So in our balcony structural thermal break, the depth of this is going to be equal to the depth of the balcony slab. Now, from a steel perspective, or just the structural aspect of a structural thermal break, there's 3 components that transfer those structural loads from that exterior structure back into that interior reinforced slab. This top bar that extends straight through the insulation, this handles tension forces. There's a bar here that rounds kind of down and then extends diagonally back up through the insulation, and that's for shear. And then these blue modules, these are full of a ultra high performance concrete. And so that's for compression. And so through that tension bar and with these blue modules acting in compression, that's taking care of your bending moment. There's also 2 fire protection plates, one on top of the structural thermal break module and one on the bottom. And then also just interesting fact about the steel to point out, the steel that extends through the thermal break is a high strength stainless steel. And then there are fusion welds at each of the steel bars that welds that stainless steel to just normal structural steel for the rest of the assembly. And the reason for that is to improve on the thermal performance. So stainless steel does have a lower thermal conductivity than structural steel by a pretty significant amount. So we achieve better thermal efficiency by using that stainless steel. It also does offer that higher resistance to corrosion. So if you do see any kind of water creep into the connection point, then you'll have that high resistance to corrosion there. And then that weld, the reason we switched to carbon steel here is for cost purposes. Stainless steel is pretty expensive, so we do make that switch for the rest of the steel assembly. It doesn't negatively impact the thermal or structural performance of the structural thermal break, so it just makes sense from a dollars and cents standpoint. And so much of the concrete examples are going to be kind of similar idea. Just the steel is typically reconfigured based on what the structure is. Now, when it comes to steel, like a steel beam through that building envelope that which maybe supports a canopy, or maybe you have rooftop equipment, really any kind of steel, any steel application that's breaking that insulation layer. We use these steel modules or insulated steel modules. If you have higher structural loads, then you need more of these. If you have lower loads, then you need less. But in effect, at your connection point, you'll have at least one of these installed at the top, one installed at the bottom of the connection. And then there are these neopore fillers that get stacked in between the structural modules. And then the whole thing gets sandwiched between two end plates. So that's what that steel application looks like.
And that's like for balcony conditions as well, or?
Sure. So if you have a steel supported balcony, you could absolutely use that steel to steel type structural thermal break. Oftentimes though, when we see a steel supported balcony, it's an exterior steel beam connected back into an interior reinforced slab. So there are structural thermal break solutions for that as well, where you have that steel to concrete connection.
Gotcha.
There's also even steel to wood connection types. A little bit less common, I'd say, as far as what we see on a day-to-day, but there are solutions for it as well.
Awesome. Yeah, the concrete one, I guess the way I would describe it, it kind of looks like a block of insulation or rigid insulation, and then you have on the top side where the tension is, you have the dowel rebars with the stainless steel. Mm-hmm. And it's interesting how you guys got the compression to go through and taking care of the shear as well. I think that's an interesting solution. That's like, if we were to detail something like that, that would be a tough problem structural wise. So that's really cool to see how all the forces get resolved through that thermal break. So that's really an interesting structural solution for in order to achieve that, since if you give
it solves two problems. One, the thermal aspect of things, to just maintaining that continuous insulation that really the architects are trying to achieve to meet building code often. But from the structural perspective, it needs to provide the structural support of whatever it's supporting. So that's where that steel comes into play, and it becomes a balance of thermal and structural performance. We're trying to use that kind of high strength stainless steel so that we can use less steel overall to mitigate any thermal bridging through that steel point, the steel points.
No, and that's great. And, you showed that product, and, as Matt mentioned, there is like rebar across the top, and I'm guessing that's customizable. The rebar is, which kind of leads me into the question. So what structural design considerations are needed when working with structural thermal breaks? Because those connections are designed often by structural engineers for the balcony connections.
Sure, that's a great question. So when using structural thermal breaks, the approach to designing your slab, and let's just focus on the concrete application for this part of the conversation, because that's really, I'd say maybe the biggest step away from the kind of traditional approach of just structural design in general. So when looking at a balcony connection, let's just take that interior slab, typically you would be designing that all as one continuous plate of the interior and exterior balcony. It's just one go. But when using a structural thermal break, you have to treat the exterior balconies as complete exterior structural elements compared to that interior slab. So in addition to being a thermal break, it's also a structural break. So when designing your interior slab, you need to make sure that the edge where you have that connection to the balcony via that structural thermal break, you need to ensure that that's going to be stiff enough to receive those structural loads from that balcony. So typically how we recommend doing it is with the balcony, you're figuring out what the per linear foot loads are on the inner edge of the balcony. So that's going to be your moment loads on a per foot basis and your shear loads on a per foot basis. And so then you apply those loads as just a line on that outer edge of that interior slab, and then take it from there with the design of that interior slab.
Yeah, and I'm guessing that you guys would work closely with the structural engineers to coordinate all that, and then there's that
Right.
back and forth, especially since it's being integrated into the structure.
Right. So when it comes to the design process and really who takes responsibility of the design of the connection, currently in the US and Canada, it is something that we do take the responsibility of designing the structural thermal break connection for projects. So we do work closely with the structural engineer. We work off of the structural plans on a project, and it's us oftentimes who are figuring out what those structural loads are at that inner balcony edge. And then we take those loads and we recommend a product that will work for those specific loads. And then we do have the back and forth with the structural engineer just for a validation that the design is works for what we proposed works for the load capacity that they are pursuing. And yeah, so that's what that looks like. I think long-term wise, we are hoping to educate the market on how to design with structural thermal breaks on their own, because as more locations, states, cities incorporate structural thermal breaks as just into their code, and it becomes more of just a way of doing things. The hope is that we can help structural engineers feel more comfortable with going at it on their own. If that makes sense.
Yeah, that's interesting. You mentioned building codes right now and previously as well. Could you explain that a little more? Is it required? Is it not required? And it seems like you're implying that maybe in the future it'll be a requirement for thermal breaks?
So we're seeing an increase in code requirements around thermal bridging recently, or in the last year and a half-ish. So 2 cities in the United States have begun to require things like structural thermal breaks at balconies and parapets and just any other kind of concrete thermal bridge through the building envelope. Those 2 cities include New York City and Seattle. So both coasts are covered on that front. And I think over the next few years, we'll start to see more areas, more regions follow suit. There's another, kind of on a higher level, ASHRAE 90.1 2019, which I recognize is these codes are more so things that architects really have to be concerned with. A lot of this relates to the building energy code, which is really kind of falls under the realm of the architect to understand and make sure that the building from an insulation standpoint is complying with that energy code. But yeah, some more codes from that perspective are starting to think about structure, incorporate language needing to address thermal bridging by requiring things like structural thermal breaks. And one of those from kind of a bigger picture standpoint, ASHRAE 90.1 2019, there's an addendum that I think will be published in 2022, but it will address thermal bridging, and any jurisdiction or location that has adopted ASHRAE 90.1 2019 and its addendums as their energy code, their building energy code that they work towards, will have to address thermal bridges by incorporating solutions like structural thermal breaks.
No, and that's great. So what you're saying right now is jurisdictionally, Oregon, correct, or Portland in particular, the authority
Sorry, I
having
think I said
jurisdiction.
Portland, but I meant Seattle. I don't know. I'm on the East Coast, and for some reason I lumped those two together. I'm sorry for listeners from Seattle and Portland right now. I always switch your cities. I meant Seattle, Washington.
Okay, so Seattle and New York are currently the authorities having jurisdictions that have vocabulary for thermal breaks right now.
Yes, that's correct. That's correct.
Okay. So, and this is just my question. When you see this as getting adopted into the code, so Matt just mentioned, he's in California, which is fairly warm. I work in Texas, and beforehand I worked in Alabama, which are fairly warm. Do you see it as, and of course you also mentioned architect, so I'm guessing it will be a building type and a building like temperature range that has to be under consideration for a thermal break to be relevant in regards to a code provision. Do you see it in that way?
Yes, it's a really good observation, because that is exactly how that addendum to ASHRAE 90.1 2019 is written. If you are in one of those warmer climate zones, it isn't something that you have to be addressing. And then the higher the climate zone, the colder the region, the more stringent the requirements are for addressing those thermal bridges. And when it comes to a building type, it's really any building type where you have thermal bridges present. So most commonly multifamily projects, or you're looking at a lot of balconies. But from other application types, I mean, any building could have a steel beam that penetrates through that building envelope for a canopy or sunshades or rooftop equipment. So it's not written specifically in a language where it's like this specific building type requires these, but if you have thermal bridges, you're in a cold region, it's going to be something to be thinking about with that addendum. And I think from a city perspective, with Seattle and New York City taking action there, I'd expect to see other cities in colder regions of the country. We also see Canada, a lot of, I think Quebec right now, their code has incorporated language for incorporating structural thermal breaks. So definitely in these colder regions, I'd see code starting to address thermal bridging more so than the Alabamas and the maybe Southern California.
No, but you actually answered it. I was going to ask you about Canada next, because I think you mentioned beforehand that you cover Canada as well. And I also cover Canada in my position now, and they have their own set of code. We're still kind of waiting for 2020 was it NBCC to come out? Yes, that's still coming out.
Yeah. So Canada is definitely a cold place. So these things like solutions like structural thermal breaks really go a long way. And they like their in Canada, they really love balconies, even though they can only use them for a portion of the year. They really take advantage of that portion of the year where they're going to be out on their balconies. So it's something that they like to have, but they also like to mitigate that kind of thermal bridging impact, any kind of heat. They want to mitigate those high heat bills. So
I had a quick question. You mentioned you were trying to get maybe in the future structural engineers to do the thermal bridging or thermal breaks themselves. How would that look like? It seems like the products you show were pretty proprietary. Or is there like a simpler solution if the structural engineer takes that capacity on? I guess, how does that look like?
Sure. So just for a maybe real life example to answer that question, we have a number of structural engineering firms here in New York City. I'm based in New Jersey, but New York City, who we've been working with for a number of years. And we do still mostly design the structural thermal break connections on those projects. But through the years, as they've become more in the know, I suppose, of our design process and review our technical information, they start to understand just really how the structural thermal breaks work more, and they are interested in knowing what our design process looks like, so they can mirror that and really just do it on their own. And so we do have software that we use that is really pretty easy to use. It's quick. I can usually bang out a project in an hour or so, just from start to finish, with designing a connection, putting the material together, and sending it off to for review. But yeah, so we have software that we use that really makes it easy. Our technical manuals, we have tons of technical information on our website that really cover a lot of the questions and design approach that we recommend taking. And then we also do things like this, where we can do some sort of, not podcast per se, but we do a lot of webinars, or we'll go into a firm and there, let's sit down and work through this, and we'll kind of teach you how to do this. And I think over time, especially with these firms that we work with a lot, that kind of learning process will just happen a little organically. And I think overall, over time, we'd like to really start to just empower more structural engineers to feel comfortable doing it on their own.
Yeah, and for any like younger structural engineers listening, what Alyson is talking about is currently these thermal structural breaks are a delegated design, but when structural engineers start implementing it into their designs as their responsibility, one of the benefits is, you don't have to do the additional review time of a delegated design. And it helps if an architect puts this request in for these thermal breaks towards the latter end of the project, there is some review time that has to go for the engineer to do a review of the connection in particular, which can take time and additional money that may not have been planned at the very beginning of the project. So implementing this when they know that the architect wants to have some sort of thermal break can really help with the project pipeline and making sure it's consistent, especially if you work in New York City, there's a lot of high profile projects, and any sort of slow down or review time, costs a lot of money. So it's beneficial to know these things ahead of time. So Alyson, we do have a lot of younger listeners kind of who do listen in, but we also have a lot of, tenured structural engineers who do listen. Do you have a final piece of advice for engineers considering, a career like yours? I know a lot of our listeners sometimes, we were talking about in Texas right now, we're having the quitting state right now, where everyone is kind of pivoting. It used to be California, Matt, but right now it's Texas. And a lot of people are really kind of looking for different opportunities. Do you have any advice that you could give someone who's maybe looking at a career like yours?
Yeah, I think my advice is to keep an open mind about where your career in engineering can go. I look back to why I originally pursued structural engineering, what my core interest was, and that was in bridge building. And so that's why I pursued an education in structural engineering. And honestly, after I graduated from school, my career just veered in a completely different direction. But it's been really great. I have kind of loved the direction of my career. I've been involved with, at a high level, I've been involved with a lot of really neat projects. I've met a lot of interesting people along the way, very well-accomplished structural engineers who are doing amazing things. And so the networking has been really great. But it's been a lot of fun. I mean, first starting off working in nuclear submarine design, designing the reactor compartments for our next class of nuclear submarine, our country's next class of nuclear submarine. I mean, that was that kind of first foray into structural engineering, to then working for a startup in the AE space that ultimately was successful. And the intent of that product was to help architects design higher performance buildings. So that was a fun experience, a little less structural engineer focused, but still fun experience in the AEC space. To now working with Schöck and kind of refocusing on that structural component, I suppose, of my tool shed. But yeah, now working with Schöck and just growing awareness of structural thermal breaks as something that benefits buildings and really just creates a better built environment. So really through the progression, just keeping an open mind of where your career can go has been something I think that's helped me really get a lot of value out of structural engineering or pursuing structural engineering in general.
No, and that's great feedback for our listeners. Every once in a while, I go on like Reddit and just kind of look up structural engineering, and you have a lot of people, whenever they've been in a certain position for a very long time, do get burnt out. And they're like, what are my options? But what you've just detailed is, you can do anything really if you want to. I mean, I did it as well. I used to be in dirt work, and I finally got to come above ground. So like a zombie.
Nice, yeah. Yeah, it really is. You can go anywhere. It's just so true.
Perfect. Well, thank you so much for your time today, Alyson. I know our listeners will really enjoy the chat, and thanks for the great content. I mean, me and Matt don't get too often to talk about structural thermal breaks. It was great to hear about something that I honestly have never really worked with closely, and I'm sure Matt feels the same.
Yeah, I appreciate it. It's just something that I hear, the people in Seattle talk about, but I'm just like, okay, we don't really do that here in SoCal that much.
Yeah. Sounds like a personal problem.
It was great to hear more about it. Yeah.
Yeah, well, yeah, thanks again for having me on today to talk about structural thermal breaks, and I'm glad it was informative.
I hope you enjoyed the episode today. We would love to hear your feedback, comments, or any questions you may have. To leave them, please visit structuralengineeringchannel.com. There you will find a summary of the key points discussed in today's episode, which is episode number 68, as well as any links to any of the resources, websites, or books mentioned during this episode. Don't forget to subscribe to Apple Podcasts, Spotify, or wherever you listen to your podcasts. Until next time, we wish you the best in all your structural engineering endeavors.